Determine the sum to n terms and hence the sum to infinity of the following infinite series with the condition that absolute value of x that's less than 1. Let us begin. So here we have a series. So let us suppose that this series is denoted by Sn, where Sn represents the sum to n terms. So we have 2 plus 5x plus 8x squared plus 11x cubed and the rest of the terms. Now this particular series, this is neither an arithmetic series nor a geometric series. It's not an arithmetic series, that's because we do not have here a common difference. We can take any term and subtract a previous term from it, and that difference is not going to stay fixed. Similarly, it's not a geometric series. That's because we do not have any common ratio here. However, this particular series is composed of two types of sequence. One will be an arithmetic sequence and the other will be a geometric sequence. So that means if we consider from the first term 2, then from the next term if we consider the constant 5, from the third term we consider 8, then from the fourth term we consider 11, and the rest of the terms. So these terms are going to be in arithmetic progression because it has a common difference. So here the first term a, so that's equals to 2, and the common difference d, that's equals to 3. We can take any terms and subtract the previous term from it. That's going to give us a common difference of 3, which means that the nth term of the sequence that's going to be given by, we have a standard formula, the first term added to n minus 1 times the common difference d. So when we substitute this value, we're going to get 3n minus 1. And then if we consider from the first term 1, because 1 is a factor of 2 here, from the first term we consider 1, from the second term we consider the variable x, from the third term we consider x squared, from the fourth term we consider x cubed. Now clearly these terms are going to be a geometric sequence. That means they are going to be in geometric progression. If they're in geometric progression, then it's going to have a first term that was defined by a, the common ratio r, that's going to be x. Then the nth term of the geometric sequence is given by a multiplied to the common ratio raised to the power of n minus 1. That means for our case, we have x raised to the power of n minus 1. Now this means that now that we have the nth term of the arithmetic sequence and the geometric sequence, we can find out the nth term of this original series. So it's a very simple task. All you have to do is take the nth term of the arithmetic sequence, but that is 3n minus 1, and to it we're going to multiply the nth term of the geometric sequence. So that's x raised to the power of n minus 1. So this is going to be the nth term of the series, and this series is an Arithmetico-Geometric series. We can verify that if we substitute n value with 4, then we have 4 times 3, that's 12. 12 minus 1, that's going to give us 11. That's multiplied to x raised to the power of 4 minus 1. That means x cubed, which means the fourth term comes out to be 11x cubed, and that's exactly what we have in the series. So now to have define the nth term of the sum, what we'll do, we'll try to find out the sum. So here we're going to rewrite the terms again. So Sn, that's going to be equals to, we have 2 added to 5x plus 8x squared plus 11x cubed. This keeps on continuing all the way up to the last term, which is 3n minus 1 multiplied to x raised to the power of n minus 1. Now here what we'll do, we will also consider the second last term. Now to find out the second last term, we have to replace the n value here with n minus 1, because n minus 1 is previous to that of n. So when we substitute n with n minus 1, we're going to get 3n minus 4. We have 3n minus 4, and to it we have to multiply x raised to the power of n minus 2. So this gives us the second last term. Now in the next step, what we'll do, we'll take the same sum Sn, and to each of the terms we're going to multiply it with the common ratio of the geometric progression. So here the common ratio came out to be x, so we will take x and multiply it with x, and let's multiply each terms with x. So the first term is 2. 2 multiplied with x gives us 2x. We're going to write it below 5x. This will become evident in a moment. Then the next term, that's 5x, we're going to multiply it with x to get 5x squared. Next will be 8x cubed. So this keeps on continuing till we reach the second last term. So here we have 3n minus 4 times x raised to the power of n minus 2. Now multiply it with x, we will get 3n minus 4 multiplied to x raised to the power of n minus 1. Added to the last term, we have 3n minus 1 times x raised to the power of n. Fine. Now what we'll do, we're going to perform a subtraction here. So we will take Sn, and from it we are going to subtract x times Sn. So this is going to give us, so we have 2, that's going to stay as 2. Then we have 5x minus 2x. That's going to give us 3x. Added to 8x squared minus 5x squared, so that's 3x squared. 11x cubed minus 8x cubed, that's 3x cubed. So this keeps on continuing. Then we consider the last term of Sn, and from here subtract the second last term of x times Sn. That's because we can here take x raised to the power of n minus 1 as the common factor. So then we have 3n minus 1 minus 3n minus 4. So that's going to leave us with 3. We have 3 times x raised to the power of n minus 1. Minus, then we have 3n minus 1 times x raised to the power of n. Okay, so this is the value of Sn minus x times Sn. We can take 1 minus x as the common factor, so that gets multiplied to Sn. This will be equals to 2 added to, now this sum 3x all the way up to 3 times x raised to the power of n minus 1. This is a geometric series. This is a geometric series. Here the first term, that's equals to 3x. We have the common ratio r, so what we can do, we can take the second term 3x squared and divide it with the first term 3x. That's going to give us, we can verify that with the ratio. We take the third term and divide it with the second term. That's also going to give us x. So here we have the common ratio as x, and we know the sum to n terms of any geometric series, that's given by the formula a multiplied to 1 minus r raised to the power of the total number of terms divided by 1 minus the common ratio r. So we'll substitute these values here. So what is a here? So a, that's 3x. 3x is going to get multiplied to 1 minus the common ratio x. Now this has to be raised to the total number of terms in the series. Now how many terms are there? So here actually not n terms, but there are n minus 1 terms are present. Let's try to understand why there are n minus 1 terms. So when we were performing the subtraction, we didn't include the first term of Sn. So that means we consider the second term all the way up to the last term. And since Sn by definition has n number of terms, so excluding one of the term leaves it with only n minus 1 number of terms. Similarly, in xSn, so here we consider the first term all the way up to the second last term. So here we have n minus 1 terms as well, because we excluded the last term. So we subtracted n minus 1 terms of Sn. We subtracted n minus 1 terms of xSn from n minus 1 terms of Sn. So that's going to leave us with n minus 1 terms in this particular geometric series. So that means we have to raise it to the power of n minus 1 whole divided by 1 minus the common ratio. So that's x minus, we have the term 3n minus 1 multiplied to x raised to the power of n. Now to find out the sum up to n terms, we're going to divide each terms on the right hand side with 1 minus x. So that's going to give us 2 over 1 minus x. Added to, we have 3 times x multiplied to 1 minus x raised to the power of n minus 1 whole divided by 1 minus x whole squared minus 3n minus 1 times x raised to the power of n whole divided by 1 minus x. So this is going to be the sum to n terms of the Arithmetico-Geometric series 2 plus 5x plus 8x squared plus 11x cubed. Okay, the sum to n terms, that is done. Now we come to the second part of the problem. We need to find out the sum to infinity with the condition that absolute value of x is less than 1. Now what is x here? So x represents the common ratio. So it's given here. In loose terms, we can say that the common ratio, absolute value of the common ratio is less than 1. So this is given to us. As this implies, let's write it down. Absolute value of x is less than 1. For this particular case, when our number of terms approaches infinity, then this implies that x raised to the power of n is going to go to 0. And also x raised to the power of n minus 1, that's also going to approach 0. Now think about this. So it's given here that the magnitude of x is less than 1, or because the absolute value of x is less than 1, which means that if we consider x to be such that it's a ratio p over q, where q naught equals to 0 and p is less than q, that in that case x is always going to be less than 1. So this is what it means when we say x is less than 1. And in that case, when x is less than 1, so as the power increases, the n value increases, so the overall ratio p over q, so that is going to decrease. And if n approaches an extremely large value, then p over q is going to go to 0. So that means sum up to infinite number of terms, this is going to be given by 2 over 1 minus x added to 3 times x multiplied to 1 minus 0 divided by 1 minus x whole square minus 3n minus 1 multiplied to 0 divided by 1 minus x. We can further simplify. We get s infinity, sum up to infinite terms, that will be 2 over 1 minus x added to 3x over 1 minus x whole square. Let's combine them. We are going to get a common denominator of 1 minus x. We're going to square this value. Then in the numerator, we have 2 multiplied to 1 minus x added to 3 times x. So we have 2 minus 2x plus 3x, so that's going to give us positive x. So we have 2 plus x divided by 1 minus x whole squared. So this is going to be the sum to infinite terms of the arithmetico-geometric series.